So very good morning all the students. Today we will see the remaining portion of the unit number 3 of the earthquake resistance design, uh, that is a Winkler model, okay, which was basically first derived by a scientist called Winkler in 1867. So basically this theory is all about the foundations, okay, which is subjected to the soft medium, okay, or we can say that a spring medium. Generally we can see that while modeling the structure in either StatPro or in any software, we have always considered the support for any foundations, okay, of the building as a fixed support. But in actual conditions the condition is totally different, okay, as because we know that the soil is having the various properties, okay, and based on the type of soil, it may be soft soil, it may be hard soil, okay, it may be medium soil, and it totally depends upon the foundation on which the soil is supposed to be there, okay. So based on the type of the soil, that is the medium soil, hard soil, or the clay soil, okay, so the Winkler has proposed the foundations model, okay, and he also derived the equation for the same, okay. So if you see the screen, the Winkler model, that is Winkler in 1867, he has basically plot the graph between the force and displacement based on the various experimental work done based on the foundation model. So we will see this part in after the completion of this slide, okay. So we will see the basic thing. So this is a Winkler model. So if you see that this is a model, okay, this is a soil medium and the foundation slab is there, and the external load in the form of P, that is a column load, or you can say that the foundation load is acting on the soil medium. So he has done the mathematical modeling. So the foundation slab as a model as a beam or plate, okay, and the soil is considered as a soil spring, okay. So this is a typical model of a Winkler. So let us see that Winkler idealize the representation or represent the soil medium as a system of identical but a mutually independent, closely spaced, discrete, linearly elastic spring, okay. So according to this idealization, the deformation of the foundation due to the applied load is confined to the loaded region only, okay. This is an important point. Then figure shows the physical representation of a Winkler foundation. So as per the diagram, if you see that the pressure deflection relation at any point is given by P, okay, that may be represented as Kw, where K is the modulus of subgrade reactions, okay. So this is a typical model of a Winkler, okay. So Q is the intensity of the load which is acting, K is the spring of a soil medium. So Winkler assumed the foundation model to which is to be consist of closely spaced independent linear spring, okay. So this is a linear space spring, okay. So if such a foundation is subjected to partially distributed surface loading, that is in the form of Q, okay, as shown in figure, then the spring will not be affected beyond the loaded region, okay. So for such a situation, an actual foundation is observed to have a surface deformation as shown in figure. So the failure pattern is like that only, okay. So whatever the portion, okay, which is to be loaded on the soil, that portion is oppositely acted as a uplift pressure, okay, in the form of from the soil, okay. So hence, by comparing the behavior of a theoretical model and the actual foundation, it can also be seen that this model essentially suffers from a complete lack of continuity in the support medium. So the load deflection equation for this case can be written as P is equal to Kw. So now this is a Winkler model, Qxy, okay, X is the horizontal, Y is the vertical, Z, okay, and it can be converted into soil spring model like this. Okay, so this is a 4 typical diagram by which the external loading can be applied on a different locations. Okay, so what are the limitations of the Winkler model? Let us see. According to the idealization, deformation of the foundation due to the applied load is confined to the loaded region only. Okay, then the number of studies and the area of the soil structure interaction have been conducted on the basis of the Winkler hypothesis for its simplicity. So the fundamental problem with the use of this model is to determine the stiffness of elastic spring used to replace the soil below foundation. That means we have to calculate the spring stiffness first while modeling this structure. Okay, then and then only we can apply the spring model in the foundations. Then next is the number of studies in the area of the soil structure interaction have been conducted on the basis of the Winkler hypothesis for its simplicity, and the fundamental problem is that to determine the stiffness of the spring. So the problem become twofold, since the numerical value of the coefficient of the subgrade reaction not only depends upon the nature of the subgrade but also the dimension of the load. Okay, so these are the some of the limitations. Then another thing is that since the subgrade stiffness is only the parameter of the Winkler model, to idealize the physical behavior, okay, of the subgrade, care must be taken into consideration so that it can be used in a practical problem. Then also the modulus of subgrade reaction or the coefficient of subgrade reaction K is a ratio between the pressure P at a given point and the surface contact of the settlement by the force. Okay, हेलो, हाँ हाँ, वो बोला कि वो क्या बोलते रिचार्ज कर रहे थे ना, तो उसका वो पैसा ले लो बोले बोलते. हाँ आ जाना, चलो चलो आता हूँ. So this is all about the Winkler model. Okay, so various theories are associated with the various foundations, okay, which is subjected to the different soil conditions. So this is also a Terazaghi equations. Okay, so we are not going in detail with Terazaghi because it is a part of soil engineering. So our syllabus is restricted only up to the Winkler model, its various definitions, okay, its properties as well as its limitations. So in your examinations you may be asked to solve the theory questions based on the Winkler models. Okay, so we will see the more remaining part of unit number 3 in our next lecture. Thank you very much for your kind attention. Thank you.